Thank you for taking time out of your busy day to join me for this Inside xtUML presentation. My name is Dean MacArthur, and the topic for this segment is creating virtual platforms. This presentation is sponsored by the organization xtUML.org. If you're unfamiliar with this online community of xtUML users, then I encourage you to visit their site, where you'll find active discussion forums and a growing library of presentations, tutorials, videos, and xtUML models. In fact, the models used in each of the presentations in this series are available at the site and can be edited using the xtUML editor that I suggest you download from the site. As part of the community's efforts to capture and share their experiences with the approach, the Inside xtUML Learning Series was established. These seminars are prepared and presented by community members. I want to remind everyone that these presentations are recorded and can be viewed later by either using the links under the Learn tab on the community's web page or by going directly to the xtUML channel on YouTube. To start today's presentation, I will try to answer the question, what is a virtual platform? And review some of the challenges that teams are encountering when creating these platforms. Following this introduction, I will summarize how model-driven development using xtUML is helping to simplify the creation of virtual platform components, and how development teams are using this approach to overcome their lack of SystemC expertise. With this background, the individual steps of using xtUML model capture and translation to create hardware components and software applications will be described. Throughout this discussion, I will refer to examples showing each approach in action and discussing how architects and designers are using these platforms to explore the complex alternatives that are available to them. To answer the question of what are virtual platforms and how are they valuable to the product development cycle, I'd like to use the context of the xtUML process. In earlier presentations of this series, the xtUML process has been described using 4 stages, namely system engineering, component design, test, and integration or assembly. At each stage, the activities performed match a unique role in the overall development of the xtUML models, while the same roles are present in general product development. In the product development context, the systems engineer is responsible for collecting requirements, identifying an architecture, and delivering specifications that will satisfy the requirements. Designers are responsible for efficiently turning a portion of that architecture and its associated specification into a testable implementation. It is this implementation that test engineering uses to validate and verify that the proposed design satisfies the requirements initially identified. Once the correctness of the design has been confirmed, then integration engineers can assemble these validated components into the final product assembly. For today's complex products, each of these roles needs tools that will allow them to perform exploration and analysis. For systems engineers, they require tools that are flexible and permit trade-off analysis. These tools must enable them to quickly capture alternatives and perform parametric tests that will deliver the data they need to make trade-off choices. For designers, they are looking for tools that help them analyze domain-specific factors such as timing, resource requirements, concurrency, and more. In contrast, test engineers have the complementary problem. They need tools that enable the exploration of connectivity across multiple domains, as well as checking for detailed functionality within each of these domains. While being able to perform testing earlier in a project is desirable, the challenge of dealing with multiple domains often makes this impractical. Lastly, integration engineers are all about detail, whether it is functionality, timing, connectivity, packaging, or more. They want to know the details. So with these roles in mind, let's look at some specific challenges today's product development teams are facing. In many new projects, system architects are presented with a new set of requirements that build on what the team has done in the past. These new requirements often include aspects that conflict with existing implementation requirements or involve new technical domains where a team expert isn't available. In either case, these factors are straining the people and the engineering practices that made the last project successful. To keep pace, many teams are enhancing their capabilities with outside expertise. They are also being more aggressive in their reuse practices. However, to be most effective, these changes require improved communication between in-house and outside team members, as well as improvements in the transfer of information between current and previous projects. Model-driven development and virtual platforms can play a role in reducing the impact of these challenges. It doesn't matter if the challenge is greatest in the software, hardware, test, or other domain. Virtual platforms can have an impact. To understand how, let's return to the 4 roles I spoke of earlier. A system engineer uses models to describe requirements and document architectural choices. A designer uses models to represent the execution environment of the design while performing tests and debug. Test engineers extend this testing using models to validate the design in terms of timing and behavior. So the execution environment that a virtual platform provides gives the architect an executable specification that can be used to actively communicate and validate requirements. It gives the designers a project-specific execution environment to test and debug their implementations in a fast yet detailed system context. To the test engineers, it provides an integrated view of the product much earlier in their test development activities. And for the integration engineers, they now have a dynamic blueprint for the final assembly that is more informative and likely more accurate than the books of specifications upon which the platform is based. For each role, the virtual platform offers improvements both in effective communication and in overall productivity. One of the earliest and currently the most widespread usage of executable platforms is in the area of hardware-software collaboration. Here, these two groups use executable platforms to document implementation alternatives and perform trade-off analysis. The net benefit derived from these efforts is that software development is able to proceed earlier in the project cycle, and the enhanced collaboration improves implementation quality while reducing the time spent addressing integration issues. In the xtUML context, the path to an executable specification and eventually a virtual platform starts with a concept. To describe this concept, an xtUML model is used to document what the system does, and by taking advantage of the executable nature of xtUML, this concept model also acts as an initial executable specification. The specification is then passed to the software, hardware, and test engineering teams for implementation. In this stage, the xtUML concept model is enhanced to describe how the system will perform the functionality contained in the executable specification. To achieve the detail needed by test and integration engineers, the xtUML implementation model is translated into a virtual platform that is essentially a software-only, platform-specific model. This virtual platform, with its detailed timing model and data representations, delivers a more accurate description of when the system performs the activities captured in the executable specification. These are details that test and integration experts require, and since the model is software only, it is easily shared across the project. Virtual platforms are a category of executable specification. They are abstract simulation models, often of the entire system of interest, and are assembled in a modular fashion from components that mimic the functionality of the product. Virtual platforms are employed heavily by software teams, so processor components and more recently multiprocessor blocks are common. And these components include instruction set simulators that permit application code to be emulated by these blocks. A key step in the maturity of virtual platforms was the release of the IEEE standard 1666 for SystemC. This standard has been selected by the industry as the preferred implementation language and has improved the availability of tools, models, and expertise. With this progress, teams are now able to provide early access to integrated system models at a time when trade-off questions are still being answered. Part of the acceleration achieved by using virtual platforms comes from the improved collaboration and communication between hardware and software teams, and this improvement extends from the system analysis stage through design and into the test stage. While this progress is encouraging, challenges remain, and the barriers to assembling a project's first SystemC Virtual Platform are high if traditional modeling practices are followed. A key barrier encountered by many teams is the lack of SystemC expertise among the team members. Some projects try to overcome this gap by purchasing standard libraries. However, these libraries contain only the most common parts and are rarely sufficient to implement the entire project. For those missing components, the effort typically falls on the domain expert, and while they have the required domain knowledge, they are rarely SystemC experts as well. This experience gap is even greater if the missing model also contains analog or continuous time behavior. This is where the xtUML approach to creating virtual platforms offers assistance. xtUML is a modeling language that permits complex behaviors to be described using a higher level of abstraction. The language is easier to learn than SystemC and is similar to the behavioral languages already used in many technical domains. Since model compilation is available for SystemC, these abstract xtUML models can be translated into SystemC components and assembled into a virtual platform with little additional effort or expertise. And since automation is used to create the SystemC components, the model implementation is likely to be more consistent, easier to understand, and of higher code quality. Now, let's dig a little deeper into the steps that make up the xtUML to SystemC alternative. The approach that I'll use today uses the xtUML process to first produce functional models that are platform independent. And once these models have been validated, then model compilation will target some components as application software and other components as hardware modules within the virtual platform. Initially, the xtUML editor is used to capture the design in terms of standard UML diagrams and the executable action language. Throughout the xtUML model creation stage, the verifier simulation environment is employed to execute the model and debug as necessary. Once sufficient functionality is available to satisfy a test, then the Bridgepoint C or C++ model compiler is used to translate functions allocated to software into C or C++ application software. Similarly, for models destined to emulate hardware modules, the Bridgepoint SystemC Model Compiler, plus the platform-specific details needed for the model conversion process, are used to translate the appropriate hardware functions into SystemC components. Once the compilation is complete, then these components can be combined with library components in a platform editor or build environment. This step concludes with a compile and link step that creates the virtual platform executable. When run, this executable will emulate the application and perform the interactions between the hardware and the software as the system is integrated. If required, changes in either the hardware or software choices can be made by going back to the original xtUML model and simply regenerating the appropriate hardware component or software function. In practice, this approach is deployed using two teams, a modeling team and a platform team. The modeling team captures and validates the xtUML models as part of the systems engineering and component design activities. When a virtual platform is required, then the platform team joins the model compilation step and platform components are generated. At this stage, the activity is handed off to the platform team, where the generated components and application code are combined with other platform elements to produce the final executable. It is the platform team that validates the integrity of the virtual platform and then distributes the executable to hardware, software, and systems engineering teams. Whether responsibility of creating the virtual platform falls on the modeling team or a separate platform team, the same steps are followed. In the next portion of my presentation, the details of creating a virtual platform from xtUML models will be explored. The xtUML executable model starts with a component diagram, which describes the partitioning of the application and the interfaces that exchange messages between the components. To describe the activities within a component, 3 layers of detail are involved. At the outer layer are class diagrams, which show data members of each class, operations to be performed on the data members, and associations between the classes. Next, inside each class, functional or data processing details are expressed in state machine diagrams and functions. Then, at the most detailed layer, are blocks of action language that describe the procedural steps that must be followed by the function, operation, or state within the state machine. Once all 3 layers have been completed, then a behavior can be considered implemented. With SystemC, the structure of the virtual platform is very similar to the structure of the xtUML executable model. For components, the matching structure is the SystemC module. Similarly, both approaches use ports and interfaces to define the messages that pass between domains, and classes to hold data structures and processing. The key distinction for SystemC is the usage of C++ as the language for describing actions and functional processing. For modeling teams that lack SystemC expertise, this distinction is also an important advantage in favor of the xtUML approach. Remember that xtUML uses the object action language, which is more abstract and much easier to learn. In addition to the advantage of entering the model at a higher level of abstraction, the xtUML approach also offers automated translation into SystemC. This translation is achieved using model compilation, which was covered in detail earlier in the series. In the case of the SystemC Model Compiler, the model is only one piece of information required to construct a platform. The other pieces are marking data, which provides customization in the interpretation of the model, and translation templates that describe how the model content are to be mapped to SystemC equivalent structures. The SystemC Model Compiler uses the same system, domain, and data type marking files as were discussed during the earlier episode. When targeting the generated models for a virtual platform, the most commonly used entries involve selecting the components that will be translated, identifying an action language function to be used if initialization is desired, and data type mappings, which are frequently used with variables that have fixed precision. Once the entries have been added to the marking files, the project is ready for translation. For consistency, I will demonstrate this approach using the same example as found in the other presentations, namely the runner's GPS watch. This is a device that monitors the distance, elapsed time, and heart rate of a runner while they are training. If you are interested in learning more about this example and how the original xtUML model was constructed, I encourage you to view the 2 episodes on creating xtUML models. In those recordings, you will find a detailed description of how the structure and functional behavior was captured. For a project like the GPS watch, a virtual platform can be helpful in answering questions on resource requirements and timing dependencies between components. Common resource questions include the effects of quantization due to fixed precision arithmetic, or the use of bit-accurate data types to increase the detail of the model. Timing dependency questions, such as race conditions or resource contention, are also good candidates for a virtual platform. In either case, finding the answers often involves lengthy simulations, and the fast execution rate of virtual platforms make them an ideal means to solve the question. The model will be my starting point, and in the following demonstration, I will show how this model is prepared for translation by the SystemC Model Compiler. The key step in this preparation is the entry of the design-specific details into the marking files. Here is a component diagram for our runner's watch. It contains 4 components: a location component for processing the GPS satellite data, a tracking component for processing the combined data and preparing results for the 3rd component, the user interface. The final component is the heart rate monitor, which processes heart rate samples. The first step to preparing the model for model compilation is to identify the components that will be translated. In this example, I will be translating the entire system. Next, I will identify all platform initialization functions and include them as markings in the domain.mark file. A common analysis question relates to the impact of fixed precision arithmetic on the performance of the architecture. These fixed precision effects can be introduced through the data type markings, where user-defined data types in the xtUML model are mapped to SystemC fixed precision alternatives. In this example, I'm specifying that the location tick variable will be represented by a 7-bit unsigned integer. Other xtUML defined data types can be mapped in a similar way. With the changes to the marking files now complete, I'm ready to run the model compiler and generate the SystemC components for the virtual platform. For this platform, I will be using point-to-point communication channels, which are exactly the same as the xtUML ports. Now, let's look at the SystemC that was generated by the model compiler. We see that structurally it contains the same components that were represented in our top-level system component diagram. There's the location, heart rate, tracking, and user interface components, all represented here in the top-level module. Once compiled in the build environment, here I'm using the Vista SystemC tool, the simulation is ready to run. Clearly, with this virtual platform, we are able to run our simulation much faster than in Verifier, and with more detail than provided by the simple SystemC executable. Within the matter of a few seconds, our virtual platform was able to emulate almost 500 seconds of performance. When investigating the performance impact of sharing a communications path among several component interfaces, the SystemC transaction level protocol is better suited than the point-to-point protocol used in the last simulation. By simply changing the marking files for the xtUML model and then rerunning the model compiler, we are ready to perform simulations to calculate utilization and identify potential contention problems in this new platform. Again, I'll be using the Vista SystemC Simulator tool to build the platform and collect the performance data. Note that with TLM models, the Vista tool stores these models in a library. Here, it's called the Bridgepoint library. These TLM components are now available to be either reused in other projects or can be configured in alternate architectures to investigate different configurations and alternate bus structures. Once the platform is built, we're ready to run. Now, since we're performing a performance test, we won't be using the human-in-the-loop interface, but rather a test that was captured during our analysis and then coded into an executable module that we now use to replace the user interface component. In this TLM environment, results of each transaction can be viewed either in a table, with waveforms, or in aggregate, or statistically, in terms of latency, distribution of delay, and distribution of number of transactions per unit time. Having used the virtual platform to investigate hardware performance and system engineering architectural questions, I now turn to the question of software development. The steps to constructing an application executable are very similar to the steps followed for creating a hardware component. The key difference is the choice of model compiler. In this case, the embedded C compiler is required. For components that are implemented as hardware, the model compiler will view them as realized components, with their associated driver code integrated into the application using the techniques demonstrated during the earlier episode on using the xtUML process with legacy code. A key advantage of describing the project's hardware and application software in this way is that when requirements change and new architectures are needed to be explored, it is the associated platform markings that must change, and not the xtUML model. This means that the model compilers can quickly create components to satisfy the new virtual platform configuration, and the project impact is minimized. In summary, this presentation has demonstrated the application of the xtUML process to the construction of virtual platforms. These platforms have become an important analysis and calibration tool for hardware, software, and systems engineers. However, the industry has adopted SystemC as the standard implementation language for these platforms, and that is a challenge for many teams. The approach that I've shown today leverages model compilers to translate xtUML models into detailed SystemC components. And as we have seen, this approach offers an easier path to creating these virtual platforms. This concludes my presentation, and thank you for joining me.